This video lecture is about the interstellar medium, the stuff between the stars. Before we begin with the lecture outline, I want you to visualize a cubic centimeter. It's a small box about the width of your pinky tip, or a little less than half an inch. Every cubic centimeter of the air you breathe contains about 2.5 times 10 to the 19th molecules. 25 with 18 zeros followed. The best vacuum chamber on Earth can get the molecule count down to about 3,000 per cubic centimeter. The interstellar medium has an average density of less than 1 atom per cubic centimeter. To look at it another way, think about sitting in an ordinary chair, leaning over and to look at the ground directly below your head. A cylinder, the diameter of your eye, drawn from your eye to the ground level, would enclose about as many particles of air as there are interstellar particles in a cylinder of the same diameter, but extending between our solar system and the center of our galaxy, 27,000 light years away. Though the space between the stars is emptier than the best vacuums created on Earth, there is some material between them composed of gas and dust. That's what we call the interstellar medium. Now, of course, there are some places in space where there's more material, like the giant molecular clouds and different emission nebula. But even there, we're talking about densities more than 10 times emptier than the vast vacuum chamber, or about 100 to 300 molecules per cubic centimeter. Also, when we talk about the Milky Way galaxy, we're talking about immense distances. So even this low density interstellar medium adds up to a significant amount over these vast scales. The interstellar medium makes up about 10 to 15% of the visible mass of the Milky Way. About 99% of the material is gas, and the rest is dust. Although the dust makes up only about 1% of the interstellar medium, it has a much greater effect on the starlight in the visible band. We can see out only roughly 6,000 light years in the plane of the galaxy because of the dust. Without the dust, we would be able to see through the entire 100,000 light years disk of the galaxy. Observations of other galaxies are done by looking up or down out of the plane of the galaxy. Dust provides a place for molecules to form. Finally, probably the most important of all is that stars and planets form from dust-filled clouds. Therefore, let us look at the dust first and then go on to the gas. The structure of the galaxy is mapped from measurements of the gas. When we observe how light scatters off the tiny grains of dust in space, we can figure out the shape and size of the grains. The dust is made of thin, highly flattened flakes or needles of graphite, carbon, and silicates, rock-like minerals, coated with water ice. Each dust flake is roughly the size of the wavelength of blue light or smaller. The dust is probably formed in the cool outer layers of red giant stars and dispersed in the red giant winds and planetary nebula. Next slide. Starlight passing through a dust cloud can be affected in a couple of ways. The light can be totally blocked if the dust is thick enough, or it can be partially scattered by an amount that depends on the color of the light and the thickness of the dust cloud. The reduction in brightness of starlight is called extinction, a killing off of the light. Not all wavelengths are scattered equally. Just as our air scatters the bluer colors in sunlight more efficiently than the redder colors, the amount of extinction by the interstellar dust depends on the wavelength. The amount of extinction is proportional to 1 over the wavelength of light. Bluer wavelengths are scattered more than redder wavelengths. The 1 over wavelength behavior of the scattering indicates that the dust size must be about the wavelength of light, on the order of 10 to the minus 5th centimeters. Less blue light reaches us, so the object appears redder than it should. This effect is called reddening, though perhaps it should be called de-bluing. If the dust particles were much larger, say the size of grains of sand, reddening would not be observed. If the dust particles were much smaller, say the size of molecules, the scattering would behave as 1 over wavelength to the 4th power. The next couple of slides show the Horsehead Nebula, which is right below the belt of Orion. This dust cloud is thick enough to block the light from the glowing emission behind it. The following slide shows the Trifid Nebula, which is just above the Sagittarius constellation. This nebula shows the effects of both dust and gas. We see the effect of extinction as the dust lanes in front of the glowing red H2 region, a glowing emission nebula. The blue part in the upper right is a reflection nebula, which is when light from a star in front of the dust cloud is scattered back to us. Since the shorter wavelengths are scattered more than the longer wavelengths, we see more bluer color scattered back to us. Observers who were behind that dust cloud looking at the star would see the star appearing redder. As I mentioned already, the red you see is an H2 region, which we came across before when we looked at star birth. H2 region is a cloud of ionized hydrogen around a hot, luminous O or B type star. The fluorescence of the hydrogen from the ultraviolet light emitted by the O and B type stars makes the nebula glow red. Recall that the H2 regions show where stars are forming. Next slide. Another famous H2 region is the Orion Nebula in the middle of the Sword of Orion. An H2 region shows where stars are forming because the stars that make the nebula light up do not live long enough to move away from where they formed. Next slide. 99% of the interstellar medium is gas, and about 90% of that is hydrogen. A small fraction of it is hot enough to glow in the visible band as an H2 region, but most of the hydrogen is much too cold to glow in the visible band. Some of the hydrogen is in molecular form, and some of it exists as individual hydrogen atoms. This cold atomic hydrogen produces a unique and very useful emission line in the radio band at a wavelength of 21 centimeters, so it is called 21 centimeter line radiation. The animation shows you that the 21 centimeter emission line is produced from what's called a spin-flip transition, when the electron flips its spin axis to be opposite the spin of the proton. It is a very small change in energy, so it's way off in the radio band. Next slide. Being in the radio band makes it extremely useful for mapping the galaxy. The Milky Way is our home galaxy in which our teeny tiny solar system is a part. All of the stars you can see without a telescope are part of the Milky Way. Most of the stars in the galaxy are so far away that they blend together to make a thin Milky Band across the sky that you can see if you are far from the city lights. The Milky Band you see is actually just a small part of the whole galaxy. That's because the dust in the galaxy's disk blocks our view of most of the galaxy. The interstellar dust limits our view in the visible band to the area within the dashed circle around the Sun, which is about 6,000 light years in radius. Radio is not blocked by the dust. Since most of the interstellar medium is made of hydrogen gas, we can use 21 centimeter line radiation produced by the cool atomic hydrogen to map the galaxy. Let's take a look at what we found after a few decades of surveys by clicking the Nice Galaxy Map link in the lower left corner. This set of 3 slides zooms in on our location in the Milky Way. Our solar system is truly microscopic at the scale of this map created by the National Geographic Society. The last slide of the set shows the 6,000 light-year circle around the solar system. Again, the entire solar system would be a microscopic dot at the scale of this map, so it's less than a pixel in this image. Now for how we create the galaxy map from the 21 centimeter line radiation. Next slide. Since radio is not blocked by the dust, we can use the 21 centimeter line radiation to map the galaxy. Different parts of the galaxy move at different speeds. The parts of the galaxy closer to the center cover a greater amount of their orbit in a given time than the outer parts. So there's a differential rotation of the galaxy disk. This differential rotation creates different Doppler shifts of the hydrogen gas. If we know how the orbit speeds change with different distances from the center of the galaxy, we can convert the Doppler shifts to distances from the galaxy center. The intensity of the 21 centimeter line radiation tells us the amount of gas. When we point our radio telescope in a given direction, we see all the different clumps of hydrogen along that direction, some close to us, some farther away. Some clumps we'll be catching up to, so we'll see a blue shift in the radio band. Other clumps will be moving faster than us around the galaxy center, so those on one side of the galaxy center as we view it from our solar system will be moving away from us and have redshifted radio emission, while those on the other side of the center from our perspective will be catching up to us and have blue shifted radio emission. Using the angle and Doppler shift, the speed, and the intensity of the 21 centimeter line radiation and trigonometry, we can systematically, strip by strip, build a map of the galaxy. This slide has a link to a high-resolution map of the Milky Way that was released in late 2016 from the H1 4Pi survey, which required more than 1 million individual observations and about 10 billion data points. The next lecture will be about the structure of the Milky Way.